So Karen Aardal is a full professor of optimization at Delft University of Technology. Her research interests include integer optimization algorithms, approximation algorithms, applications of machine learning, and the modeling and resolution of problems within energy and healthcare. She is a former chair of the Mathematical Optimization Society, which is actually the umbrella under which these dots are now held. Well, the Mixed Integer Programming Society, which is under the Math Optimization Society. She served on the board of the Informs Computing Society in 3 periods. She served on several editorial boards, such as Math Programming Series B, Informs Journal and Computing, and OR Letters. And in the Netherlands, she is serving on the board of Domain Science of the Dutch Research Council NWO. We are very pleased to have Karen here. We were very much pushing for her to attend, even though the time difference maybe does not make it super convenient. So thank you very much for joining us. And please go ahead.
Thank you very much, and thank you for inviting me. And I wanted to participate or to give a talk for quite a long period, but it was like a matching problem to get it to fit in. So I'm happy that it worked out in the end. So today I'm going to give you a little bit like a helicopter view of some recent developments on the interface between integer optimization and machine learning. And of course, we have several experts here in the audience. So I hope you're not going to feel too bored during the presentation. Even though it's a short talk, I still have divided it in 2 parts. One is really going to be around some machine learning results to enhance elements of branch and bound, basically. And in the second part, I would like to show some relations between discrete math and deep learning. Actually, you're not going to really see the discrete math, but it's used in the proofs that are behind the results that I'm going to show to you. So just very briefly, whatever I'm going to talk about further on is valid for mixed integer optimization, but I just wanted to make it a bit more clean here. So I'm showing you an integer optimization problem. So I'm assuming minimization here. This is the LP relaxation. X is now going to be a real valued vector. Actually, it's going to be a rational vector because I will assume that my input is rational. So the algorithm that most of us use to solve this problem to optimality is branch and bound. And the engine of branch and bound is, of course, to solve the LP relaxation. During the algorithm, we are going to maintain the value of the best feasible solution found so far, and that has value z bar. And now, so branch and bound, as I describe it here, I don't describe an algorithm, but more like a framework. So if we cannot prune a node in our branch and bound tree, we need to choose a variable, xj, that in the LP relaxation has a non-integer value, so xj hat. And notice that I say choose a variable, and I don't tell you how this choice is going to be made right now. And then we subdivide our feasible region by imposing different constraints. In the down branch, we say that xj should take values less than or equal to xj hat rounded down, and in the other part, we ask for xj being greater than or equal to xj hat rounded down plus 1. So branch and bound is much more than just building a search tree. And there's been several decades, probably since the beginning of the 90s, we really saw these professional softwares where you can, where you had subroutines doing various things that not everyone doing computations had to do, implement their own version of the simplex algorithm, and so on and so forth. So during these past decades, it has been an enormous development in optimizing these frameworks. So all of them, they include several sort of modules. We start with some pre-solved, where you typically take out redundant constraints, you improve bounds, you massage the problem a little bit. And that can have actually quite an impressive impact on the solvability. We have heuristics to find good feasible solutions, which improve, of course, the upper bound, and cutting planes, as you just heard, to improve the lower bound. And of course, in branch and bound, what you want is, of course, that these lower and upper bounds get together as quickly as possible, because then we have a smaller search tree. And then we have advanced algorithms for variable and node selection problems that I'm going to describe soon. So the question then is, can we use machine learning to learn any of these components? And what you have to be aware of is, of course, in a package like Gurobi or Skip or whatever you use, all these modules are linked together in a very sophisticated way, so they provide each other with information. And if you sort of substitute one of them with your learning thing, then you typically don't get access to the rest of it in the same way as the internal modules of the software does. So that can make it even harder to compete with the software. What I'm going to talk about further in this part one is basically based on this fairly recent overview or survey paper, if you like. The main author is Lara Scavuzzo. She's a PhD student of mine in Delft, and then also Andrea Lodi and Neil Yorke-Smith have been working together with us on this. There are a couple of other surveys, and I hope I don't omit anything that someone is going to be upset with me now. So I mean, it's a short talk here, so I cannot be completely covering everything, but I'm mentioning 3 ones. Andrea Lodi and Giulia Sarpellon, they have a survey already in 2017 on learning to branch. Benjo and co-authors from 2021, which is a more methodological overview, and then Desai and Khalil here present on directed towards cutting planes. That is also recent from 2023. And there are most likely several others, but at least for the people who want to enter the field, I think these are good starting points. Okay, so the learning tasks where we could maybe do some learning within a branch and bound framework is the variable selection problem, the node selection problem, and heuristics, cutting planes, configuration decisions, including pre-solve. Of course, in a package like Gurobi, there are zillions of parameters that could be set that could also be trained for the problem type that you're looking at. Given the limited time, I'm going to focus on the branching variable selection problem because probably most have been done there. So this problem is, as I mentioned in the beginning, I said choose a variable to branch on. And depending on what you do here, it can have quite a dramatic impact on the search tree. So the node selection problem is the problem that, okay, you have a tree at the current point in time, and you have some nodes in your branch and bound tree that haven't been evaluated yet. And the question is then, which is the next one in line to be evaluated? That's the node selection problem. So as I said, it's not easy to improve on what the best solvers already do. This is a picture from quite an old paper, but it's just to illustrate what the challenges are. This is from a paper of 2013 from Achterberg and Wunderling. So they wanted to see what the progress was between CPLEX version 6.0 and 12.5. So that is on the x-axis here. They solved, so they implemented on the same machine these different versions of CPLEX, or the same machine type. And they looked at what the speed up was. So this speed up is just algorithmic speed up. It's not hardware speed up because it's done on the same machine type. And they looked at instances from their own internal library. So these are not accessible for mortal people. It's their own database. And they looked at problems that can be solved in the interval of 10 seconds to 10,000 seconds, and by at least one version of the code. And here, the red line illustrates the time speed up. So you see you get up to a factor of 90 speed up from version 6 to 12.5. So this is in the time span of 1998 to 2012. On the left-hand side here, you see the number of timeouts. So the number of instances in this database that could not be solved within this 10,000 second time limit from version 6 to 12.5. And you see, of course, quite a drastic decrease in the number of instances that timed out. So this is what you're up to. And of course, this is ends in CPLEX 12.5. Now we are much further, and the improvement has continued. Maybe not that drastically as here, but still. So let's have a look at the branching variable selection problem. So if you can't prune, you need to choose a variable to branch on, and which fractional variable should you choose here? As I said, this has a huge impact on the size of the resulting search tree. So what are in the current systems that we have? Well, there are many rules, and to be honest, some of them are also kept fairly secret. But if you read the literature, you see there are basically 3 rules that you can see what explicitly is going on. The pseudo-cost branching keeps a history of the objective gain per unit change in the variable value. Strong branching really explicitly computes the progress in objective value for each fractional variable. So for each candidate variable, you solve 2 LPs to see what happens in the down branch and the up branch, and you choose the variable that gives you the best progress in the dual bound. Because the pseudo-cost branching keeps a history, well, if you start, you don't have any history, so you need to start somewhere. So reliability branching, then you start with pseudo-cost branching and you turn to, or you start with strong branching and you turn to pseudo-cost branching, which is cheaper once these pseudo-costs become reliable. Then you have something called hybrid branching, which is not completely clear to me what is going on, but it's a combination of many rules also from the constraint programming and SAT communities. So there, of course, it's not really a theorem here saying that, okay, use strong branching, it's always best, but it really depends also on the problem type. But I think the empirical results seem to indicate that strong branching results in the smaller trees, but it is costly. So the drawback is that it is very heavy. Maybe good to point out that all branching is actually done on single variables. So xj less than or equal to something or greater than or equal to something. And from theory, we actually know that the best thing is to branch on more general disjunctions, but this is not so easy to implement. And of course, also all the stuff going on inside of a branch and bound framework typically keep information regarding variables and not regarding functions. Okay, so some papers that got the machine learning related research going, and now I'm only thinking about the variable selection problem here. So I think, and that one of the papers that also appeared really in an optimization paper in 2017 in From Journal Computing is by Marcos Alvarez, Louveau, and Vehenkel. The working paper is from 2014. They really did offline learning of the strong branching score. in the same year, the same authors also did an online version. So they started with strong branching, then while online, they imposed a learning algorithm, and they use this in a sort of reliability branching style. So they start with computing the strong branching score until the learned score seemed to be reliable. Shortly after that, we have the paper by Elias and co-authors. They also did online learning, but did not explicitly compute the strong branching score, but was using learning to rank. So the question is, what is the best variable to branch on, and not computing the strong branching score explicitly. Okay, so these papers basically kept a feature vector for each variable. And later on, Gus and co-authors, they used a different representation. So they have a bipartite graph representation of the MILP. So here you have your formulation, and then they kept the bipartite graph where sort of the left side set of the nodes in the bipartite graph were associated to the constraints. So they had one node for each constraint, and the nodes in the right part of the bipartite representation were variable nodes. And the weights on the edges between them were just the coefficient, the corresponding constraint coefficient. And this actually was very nice. Also, this data structure can be parsed by a graphical neural network. And they use this to do offline learning of like a problem type branching rule. So again, it was basically not, I think, the explicit strong branching score, but some kind of ranking thing that would do prioritize the variables in the same way as strong branching would do. There are some drawbacks with learning from an expert. So these, of course, here we use some expert, in most cases inspired by strong branching. And this is not every problem type strong branching is effective on. So if the LP relaxation doesn't really provide you with good information, then strong branching is probably not going to be the best thing to do. And then you can learn it, but if your expert is already not so good, then what you learn is also not going to be so good. Training is going to be quite expensive if you really want to explicitly use the strong branching score. And as I said in the beginning, your strong branching score is not going to profit from the internal information provided in the by, say, Gurobi, Skip, or whatever you do. So you cannot benefit from it. And so even if you do a very good job, you might still have a struggle to compete with the current algorithms. And then it's still like, say, strong branching isn't really going to work. What are you going to do then? Or like, I think it's also an issue in the sense that when we test these things, most of the time we test, say, on MIPLib, but MIPLib is hugely heterogeneous. It's very different kind of problem types. So it's very hard to really train a function to perform really well on MIPLib, because the instances look very differently. So I think also what Bartolomeo hinted, like if you have more like an industry kind of application where the instances seem to look more or less the same, or at least have the similar structure, then it's probably going to pay off much more. But the question is, can we learn without expert knowledge? And then the answer is yes. There are some reinforcement learning approaches, one from 2020 by Etev and co-authors, and one that uses a slightly different type by Lara Scavuzzo and co-authors from NeurIPS 22. So both of them use reinforcement learning. Let me see how I'm doing. I have to speed up a little bit. So Eteven et al., they have the observation that if you use the depth first search in your tree, then if you minimize the subtree size at each node, then you end up by minimizing the total branch and bound tree size. So the rewards were basically approximating the local subtree size. Lara and co-authors use a more general tree MDP framework, which gives a very nice way of giving the rewards within the reinforcement learning framework. So when in the computational results, they see that for instances where strong branching struggles, then this reinforcement learn-based tree MDP framework works nicely. So I think I have about 5 minutes or so left. So I will spend these 5 minutes shortly saying something about this, because this is very different. So in the previous part, we looked at things more of an empirical flavor. And in this part, we are looking at theoretical results where pretty nifty discrete mathematics, really theory of polytopes and so on, is used to prove these results. And I'm basically focusing on one paper, but let's just see for people who are not used to neural nets. So this is a K+1 layer deep neural network. We have an input layer, we have K hidden layers and an output layer. So this is an acyclic directed graph where we have weights on the nodes and the arcs. And the number of nodes in the input and output layer is, of course, related to the problem that you want to solve. So suppose we can take one of these very well-known examples, namely recognizing written numbers. For this is from the MNIST database. So then the input, the number of nodes in your input layer is going to be the number of pixels in the image. So just indicating if it's a black pixel or a white pixel. And the number of output nodes is, of course, the number of possible outcomes. So it could be a number between 0 and 9. So you have 10 output nodes, and the number of input nodes is like 30 times 30 or something like that. Okay, and what goes on in such a hidden layer? Here I have just focus on node J, and node J gets information from several of its predecessor in the network, and I highlighted just one of them, node I. So this arc going from I to J has a weight, Wij, and in node J we have a bias, and we have what we call an activation function. And the output here, xj, is going to be what the activation function outputs from the sum of Wij xi plus this bias bj. And we need this to just make it different from just regression or something like that. So example of activation function very well known is the ReLU, like the rectified linear unit. It just takes the maximum of 0 and exits off. The step function is another one. Just if it's less than or equal to 0, we get 0. Otherwise, we get 1. We have the sigmoid function and so on. There are many versions, but I mentioned these because the papers are analyzing these two specific cases. So let's skip the next one because I guess you know what it looks like. So just some definition here. The size of the neural net is just the sum of the width. So you have the input layer, then we have hidden layers, K of them. The number of nodes in this hidden layer is Wi. And if you sum them all up, it's the size of the neural net. The depth is the number of hidden layers plus 1. And the width is just the maximum width of all the hidden layers. So this is the paper I'm referring to is by Aurora Basu, Mianji, and Mukherjee from 2018. So they looked at expressiveness. So what kind of family of functions can you represent using a ReLU DNN? And of course, every ReLU DNN represents a piecewise linear function. That is not very surprising, but they also show that every piecewise linear function can be represented by a ReLU DNN with at most the logarithm of n+1 rounded up +1 depth. And here they really needed quite a lot of machinery from discrete math. Yeah, function. I don't know how I'm doing. Maybe 2 minutes still or something like that.
Yeah, you can do 2, maybe just a more, like 5 minutes is also okay.
Yeah, I will be done certainly within 5, no problem. Okay, so they have also some trade-off between depth and size of the network. So here they analyze the case where the input and output dimension is 1. So they have 1 input node and 1 output node. And then they say that, okay, for every natural number n, there exists a family of functions such that for any function f in the family, we have that f can be represented by a ReLU DNN with n squared hidden layers and of size n cubed. So size is just the sum of the width. But it is not representable by a ReLU DNN when you take down the number of hidden layers. Then you need an exponential increase in the size of the network. So there are hard functions which, if you try to represent it in a shallower DNN, then you would need exponentially larger size of the network. And then the training, so solving the empirical risk minimization problem, they also did, so here they developed a specific algorithm for the training. So you have D data points, so input and output, and then you want to minimize the loss function or the average loss. Such that it's representable by a ReLU DNN with 1 hidden layer. So the size is W. And then they have the algorithm. Here you see the runtime. I can read it, but you can probably better just read it yourself. And you see that if the width or the size of this network is a constant and n is a constant, then it has polynomial running time in the data size for fixed n and w. And later on, Amitabh Basu, so he's one of the authors here, together with a PhD student, Sami Khalif, at last IPCO, they obtained similar results for the step activation function. So then you get even more clean results, that instead of this, in this first representability result here, you can represent it with 2 hidden layers, for instance. So they get sharper results when they look at the step function. And I think this is a very good time to say thank you.
Maybe we have time for one quick question, everyone all together, and then we go to the breakout rooms. If not, then let's thank Karin and Bartolomeo one more time. And I'm going to stop the recording. And I just wanted to say before I do that we have 2 more dots in the coming months. Last Friday of the month in March, last Friday of the month in April. So stay tuned. Even if it doesn't come to your inbox, put it on your calendar. We will put it on the dots calendar, which is available on the website. So you could add that to your calendar, and it'll be the well, we hope to see you there. Thanks everyone for coming.